In this video, we're going to do something rather exciting. We're going to introduce two more functions. Well, they're actually both examples of trigonometric functions, but nonetheless, we're going to introduce two functions, the sine function and the cosine function. I don't want to spoil too much about it. We're going to generate the graph of the sine and the cosine function, and we're going to talk about their properties. But I will say it's necessary to introduce the sine and the cosine function because of what we're trying to investigate later in the unit. We're trying to study or model periodic behavior, okay, which is something we talked about in the previous lesson. And because you want to study or model periodic behavior, then bringing up the idea or talking about sine and cosine functions becomes a necessity. Okay, so you know what? Let's start with sine first. Okay, so we're going to complete the table and round y to 2 decimal places if necessary. And then draw a smooth curve, so we have the graph below. So hopefully you didn't forget your special values. Yeah, so everything here I'm going to fill in is based on what I learned from the previous unit of special angles. So like 0 degrees, sine 0 is 0, so it's 1/2 root 3 over 2, 1. And then based on the cast rule, the second quadrant will also be positive. Beautiful. And we're entering the third quadrant, which means sine is negative. Fourth quadrant, sine is also negative. Oops. It's a bad, not a bad habit, it's a good habit. I am so used to special angles, exact values. So it's, well, it's up to you. I'm going to leave it as root 3 over 2 because I love special angle. I love exact values. So if you want to round 2 decimal places, you can write 0.87, okay? Because root 3 over 2 is 0.866. Let's see. Yeah, 0.866. So 2 decimal places, 0.87. But I'm going to leave it as root 3 over 2. I love my exact values. Okay, it's 330 degrees. That's -1/2. And then we're back at 0. So now I'm going to cheat a little. So for 390 degrees, I'm just going to look at the answer for 30 degrees because what's the relationship between 30 degrees and 390 degrees? They are coterminal, which means the ratios are going to be equal. So keep looking, I guess, a diagonal, like top right. All right. All right. So hopefully you got the exact same values. We will now plot those points and connect the dots. Okay, so 0. So this is 0.87. So 6, 9, 6, 7, 8, 9. So we're looking at about there. Beautiful. Oh, so pretty. So I'm going to give, let's keep going, why not? Because I have the table. I'm actually not using the table, but 0.877, oh, 0.87, sorry. Oops, oh man, I missed a dot. Well, that's not very good. I'll tell you how I knew I was wrong. Well, there's multiple reasons how I knew I made a boo-boo there. But one of them being, well, first, the easiest reason is that the numbers don't match up with the grid, because at 720 it should be back at 0. Another reason, it just doesn't look like a beautiful symmetrical wave, which is what we're going to get when you connect the dots. So it's a good mistake, actually, because I want to bring up the fact that when you graph these sine or cosine functions, what you should have in mind is a beautiful, smooth, symmetrical wave, okay? So when I connect these dots, please don't like make it sharp. It's a nice, smooth, symmetrical wave. Smooth, symmetrical wave. And if you're studying advanced functions next year, you're going to do this exact same thing. Okay? You're going to study the sine and cosine function again next year. Beautiful. Beautiful. Very pretty. Okay, so hopefully you got the exact same graph as I did. Now, remember to add arrows because the sine function does go on forever. Why does it go on forever? Well, I can have any angle. I can rotate counterclockwise or clockwise. Remember from the last unit? I can rotate multiple revolutions, so I can have a very, very large positive angle. That means a counterclockwise rotation. And then you can have a large negative angle because now you'll be rotating clockwise. So there's really no restriction your angle can be. So that's why I add arrows here, arrows here. All right, so now let's do the cosine function. Okay, so this time, even though it's around 2 decimal places, I'm still going to do root 3 over 2. I just love my exact values. So hopefully you don't mind, but you can write 0.87. Okay, quadrant 1, cosine is positive. Quadrant 2, cosine is negative. And then quadrant 3, we're still negative. And then quadrant 4, we are positive. And then coterminal angles, so copy the, so for 390 degrees, I'm going to copy what I wrote for 30 degrees. And then keep going. Coterminal angles, very, very nice. All right, let's plot our points here. So once again, smooth, symmetrical wave. That's what I'm thinking of when I graph the sine or cosine function. Oh, did I make a mistake again? Nope, that's beautiful. Beautiful. So at 360 degrees, I don't want to spoil the words, but I fulfilled one cycle. I graphed one cycle. We're going to talk about the properties in a second once I finish plotting these points. Okay, let's connect the dots here. Smooth, symmetrical waves. Oof. That's bothering me. Let me fix that. Yeah, that's good enough. All right, beautiful. Can you see the arrow there? There we go. All right, so I grabbed the sine function and the cosine function. So you can pause the video for a second. I want you to stare at the sine function, stare at the cosine function, and then try your best to fill in the properties. Okay, fill in the properties for sine and for cosine. Okay, so when you're done, unpause the video. So hopefully you've done it already or tried to do it. So hopefully you've noticed that the properties for the sine function and the cosine function are very, very similar. In fact, many of the properties are exactly the same. There are more similarities between sine and cosine as opposed to differences. And I'll explain why. So what's the maximum and the minimum value for sine? So max is 1, minimum is -1. That makes sense. Because where are we getting these numbers from? We're getting them from the unit circle, right? Sine is defined as a y-coordinate of the point on the unit circle. So yeah, the max is 1 and the min is -1. And cosine is defined as the x-coordinate of the point on the unit circle. So it's 1 and -1. Beautiful. Amplitude. In the last lesson, we said amplitude is max minus min divided by 2, right? So max minus min over 2. Well, guess what? The max and min values are the same for both sine and cosine. right? They both have a max of 1, a minimum of -1. So, 1 minus -1 over 2, which is 1. So they both have an amplitude, right? If you look at the graphs, half the distance between the max and min values, they're both 1. Okay. Just looking at the waves, they look so similar. What about the period? Well, the period, as you can tell from the tables that we filled in, the period for both are 360 degrees, which once again makes perfect sense because think about the unit circle. Well, it's after 360 degrees, I'm getting the exact same ratios. I'm recycling the same numbers after every 360 degrees because I'm working with a circle, right? I'm not working with a semicircle, I'm working with a circle. So yeah, 360 degrees. So domain, I already spoke about the domain. So for domain for both is all real numbers, okay? No restrictions. You can have a large angle, a negative, like large positive or negative angle. You can have 0 degrees as your angle. So no restrictions. Range. So we spoke about the maximum and minimum values, and they should have the same range. So in both cases, you'll have a wave bouncing around from -1 to 1. All right, so we talked about a lot of similarities. In fact, there's one more thing which is similar, which is called the equation of the axis. So draw the wave again. Let's do the sine wave, okay? So that's the sine wave. What's the equation of the axis? It's that midline which divides your wave into a top half and a bottom half. Okay, it's that, oops, you can't see. It's that midline that divides your wave into a top half and a bottom half. That's the equation of axis. In fact, some people call it the like the midline. Okay, you have to state the equation of the midline. Some people call it the central axis, but I believe the textbook that we're using is calling it the equation of the axis. Doesn't matter, you call it the central axis, call it the midline. No matter what you say, the equation will be y equals 0. Okay, it will be the x-axis. That will divide your beautiful wave into a top half and a bottom half. Okay, so wow. Right now it seems like sine and cosine is the same function, okay, but clearly they're not. So what is different about the two? And it's the intercepts, okay? So the sine function starts on the equation of the axis, okay? So the y-intercept is 0. But the cosine function starts at a maximum value of 1. So basically we're looking at the exact same wave, they just have a different starting point, okay? Now, what about x-intercept? So this one's a little tricky. For the x-intercept, you might be tempted to say for the sine function that the x-intercepts are 180 degrees, or 0, 180, 360, 540, and 720 degrees. You might be tempted to say that. But in fact, you should understand if you looked at this wave, it goes on forever. There are an infinite number of x-intercepts. Not 1, not 2, not 3, an infinite number. This wave just goes bouncing back and forth from -1 to 1, just bounce, 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 bounce. So there's an infinite number of x-intercepts. And there's a pattern at where the x-intercepts occur. They occur, the first one occurs, you can imagine, at 0. And every 180 degrees, you'll reach another x-intercept. And you can go left, you could go right. So the fancy way of writing it is 180 degrees times n. And n, the restriction on n, is that it's an integer. So as long as you let n be an integer, like -1, -2, -3, 0, 1, 2, 3, then the next intercept. So I don't know, let's say, so we'll do 180 times 8. So at 1,440 degrees, sine of 1,440 degrees, you'll be at 0 because it's a multiple of 180. Now for cosine, it's a little different because if you stick close to the vertical axis, you'll see that the first x-intercept, you can say 90 or -90, but we're going to pick 90 degrees. And every subsequent x-intercept will have to be a multiple of 180 from 90 degrees. So it's plus 180 degree n. And same idea as before, n is an integer. N is an element of the integers. I know the notation is a little weird or a little different, but it's because there are an infinite number of x-intercepts. And you need some interesting notation to deal with that problem. So yeah, that's basically it for the two new functions for the course, sine function and cosine function. There's no homework for this, but I guess the homework is to not memorize the properties, but understand where they're coming from. Okay, really refer to the unit circle for majority of these properties. In fact, all of these properties can come, you can just think about the unit circle. And yeah, of course, you need to know how the sine and cosine functions look like, because what we're going to do in the next lesson is transform them. So you need to know how the sine function looks. So there's no homework assigned for this lesson, but I will strongly recommend that you please don't memorize the properties of the sine and cosine function, but understand where these numbers are coming from. And for a large majority of these properties, you really want to refer back to what you learned in the previous unit, when you're, especially like when we're talking about the unit circle. So it makes sense that the max is 1, and it makes sense that the minimum value is -1. And I think the hardest property for students to understand is really the x-intercept, because there are an infinite number of them, and we have to introduce this notation. So I'll show you a quick diagram here. Let's go back to the sine function. It makes sense. Every 180 degrees, you're at an x-intercept. Okay, if you envision that the first one occurs at 0 degrees, to reach the subsequent ones, you have to just go 180, 180, 180, 180. For the cosine function, you're thinking the first one starts at 90. Okay, you can technically start at any value, but we're gonna start at 90 plus 180 plus 180 plus 180 plus 180, and so forth and so on. Okay, so that's where that notation came from. So definitely understand all the properties of sine and cosine function. And tomorrow, or the next lesson, we are going to transform the sine and cosine functions. So because we're doing that, it's imperative, it's critical that you know the general shape of the sine function and the cosine function. Because if you don't know the general shape, then you'll have absolutely no clue how the transform function is going to look like. Okay, so that's basically it for sine and cosine functions.